So we're going to start by talking about functions, but before we talk about functions, we're going to talk about relations. A relation is just a set of ordered pairs. So a lot of this is going to be review, things you've heard before, but it's good to bring back these ideas. So you're going to see relations sometimes that aren't functions, and that's what we call them. So things like you could have a circle. A circle is a relation. Not a very good circle, but it has an infinite number of ordered pairs around the circle. Like you can't list all the ordered pairs that are on that circle, right? But all the points are equidistant from the center of the circle. So that's the definition of a circle. It's a set of ordered pairs. There's an infinite number of ordered pairs, but that's okay. It's still a relation. You could have a line. A line is a set of ordered pairs. It's also a relation. There's an infinite number of ordered pairs on that line. But you could also have just a set of ordered pairs, like you could have the point 1, 2, and the point 1, 4, 1 comma 4, just those two ordered pairs, and that would be a relation, okay? So any set of ordered pairs is a relation. Now, in order for it to be a function, each first component, and I'm going to call it first component. The actual name is abscissa, but people don't remember that. So the first component can only map that's supposed to say map, to one second component. And the second component is called the ordinate, but if you really want to know those names. So this is the abscissa, and you're going to think of it probably as the x values, because a lot of times we talk about ordered pairs in terms of x comma y. But they don't have to be in terms of x and y. In the real world, it's not always a matter of x and y. The second component is called the ordinate. But again, a lot of times people don't remember those. It's not a big deal. You just have to remember, you know, there's a first part to the ordered pair, the first component and the second component. So in a function, you can, each first component, it can only map to one second component. So in our circle here, this is not a function, because you've got overlapping occurring. You've got, you know, if you put this on a grid and you said, well, here's my x value, there's 2 points where it's crossing, right? Okay, so it's mapping to 2, that x value is mapping to 2 different y values. The line is a function. So each x value, if you put it on a coordinate system, each x value is only mapping to one y value. Not all lines are functions, but that one is. Our last one, example of a relation, what do you think? Think it's a function or not a function? Well, it's not a function because you've only got 2 points, but they both have an x value of 1. The first component's 1, and it's mapping to 2 different second components or 2 different ordinates. So this is not a function. Oh, dear. Sometimes things like that happen. Okay, so that was just a little bit about relations and functions. So I want to try to get through the vocabulary in this video. Notation. For the notation, we write f of x, or f at x, or f evaluated at x, f in terms of x, something like that. It is not f times x. It doesn't have to be the f notation. You can have functions, you have g of x or h of x. Sometimes they'll use capital letters. This allows us to talk about different functions and give them different names, so that's good. Just a little bit more on the notation. Remember, if you have the inverse of a function, we're going to talk about inverses in a little bit, then that is f inverse of x, and it has that notation with it's not an exponent, it's read f inverse of x. Okay, so inputs and outputs. So when we say f of 7 equals 15, we're talking about an input of 7 and an output of 15. So one, we're placing something in the function machine, a value, an expression. It could be a variable, could be a number, could be a monkey with a banana. And then you get this output. Okay, so this idea of inputs and outputs, because we're going to talk about that sometimes. All right, so just a little bit more review here. Domain is all the first components, or the inputs. I should have said inputs. And the range is the outputs. Okay, it's a set of, the domain is the set of the inputs, and the range is the set of the outputs. Okay, what else do we have? The vertical line test. So you might remember this. So remember a minute ago we had a circle, and you could say the circle does not pass the vertical line test because when we draw a vertical line, it hits in 2 spots, and therefore that is not a function. The circle is not a function. I didn't make an equation for a circle, but we could. Okay, so let's say you have something like this, and you have kind of this relation, set of ordered pairs like that. Is it a function? Does it pass the vertical line test? Well, the answer is yes, this is a function. So this part's a function. I shouldn't put them on the same grid. You can draw a vertical line. It doesn't hit the open circle because it's an open circle, so it's okay. This is not a function. We already talked about that. Okay, but that idea of a vertical line test. So I've switched in my video making, trying to go to a different format here. I don't know if it's better, but we'll see. One-to-one functions. One-to-one functions, they have to pass the vertical line test to be a function. And then they have to pass the horizontal line test to be a one-to-one function. So let's say I have, let me see if I can bring this over here. Let's say I have a function that looks like a parabola. Okay, passes the vertical line test, it's a function. I already said that it was a function, but it's not one-to-one because it doesn't pass the horizontal line test, meaning if I draw a horizontal line, it hits in more than one place. So let's say we have something else. Let's see. Let's say we had that one a minute ago. I'll make it a little bit different. So you have something like this. Is that a one-to-one function? Does it pass the vertical line test? Yeah, it's a function, so yes, it's a function. It passes the vertical line test. Now, some of you might be concerned and you might say, well, but what if I draw a vertical line right here? Say I draw a vertical line right there. It doesn't hit any points, right? That's okay. It doesn't have to, we don't have to have a point at that value of x. It's just not defined for that value. Doesn't mean it's not a function. So passes the vertical line test. Does it pass the horizontal line test? Is it a one-to-one function? Yeah, it's a one-to-one function. So passes the horizontal line test as well. So it's a one-to-one function. That was exciting. So we could do more. All right, now local minimums and maximums and absolute minimums and maximums. So let's say we have something, a function that looks like, something like this. And when we talk about a local min or max, we're not talking about the extremes at the ultimate high and low of the function. We're just talking about in the neighborhood. Is it a min or is it a max? So right here, we would call that a local min. because in the neighborhood, in that area, that is the lowest point. Now we would call this up here a local max. Same thing, it's in the neighborhood, and so that's the highest point in the neighborhood. Now, what about absolute min and max? Well, the absolute min is right here. That is the lowest point, the lowest output that we have. For the whole graph, the whole function, that's the lowest one, the lowest minimum value that we have right there at like -4. That would be the absolute min. But the absolute max, it doesn't have one. You'll notice that this part just keeps going up and up and up, so there is no absolute max. Okay, so it doesn't, we don't have a highest value, it just keeps going and going, and that arrow indicates that. Okay, so I think that takes care of the vocabulary and some review. So I'm going to end this video.